Brian Caffo, and this is the lecture on multivariable regression examples. This is part of the Coursera Data Science specialization, co-taught by my co-instructors Jeff Leake and Roger Peng. We're all in the Department of Biostatistics at the Johns Hopkins Bloomberg School of Public Health. Okay, so let's start with the Swiss fertility data again, or not again, but let's start with this. And to get this data set, you just do library data sets, and then data Swiss, require the package stats and require the package graphics to get this nice pairwise scatter plot here. And this is from the, I believe this is from the help file for the Swiss data set. At any rate, this is a nice way, it's probably better to blow it up, but this is a nice way to investigate the relationship between all the variables in this data set. Let me go one step further and show you the help file. So if you do in our question mark then Swiss, if you do that command right there at the after you've correctly loaded the datasets package, then it tells you about this dataset, and it's the standardized fertility measure and then a bunch of related socioeconomic indicators for 47 French-speaking provinces of Switzerland in about 1888. It's kind of a famous data set. So our outcome that we're interested in is fertility, all 6 variables are expressed in terms of percentages from 0 to 100. And so one of the predictors we want to use to predict fertility is the percentage of males involved in agriculture as an occupation. We want to include the ones who receive the highest mark on any Army examination, and so on. There's the education beyond primary school, the percent Catholic as opposed to Protestant, and then infant mortality. And then it says all but fertility give proportions. So anyway, you can do help data. It helps Swiss to learn more about that data set, though it mostly just contains that file, but it also gives you some references, I believe. Let's just do the first thing that we might think to do is we want to use these variables to predict fertility. So why don't we consider a linear model with no interactions? And if you do a tilde and then a period, then that just includes all the variables in the data frame as predictors. And this data equals Swiss just says look in the data frame Swiss for everything. And then when you run it, summary just runs the output. It's usually, by the way, preferable to assign your output to a variable and then do summary of that variable, but so it all fits on one line. I do it this way. And here's our coefficient, and here's the table, here's our coefficients, and we get, I want to point you to this number, negative 0.1721 right there for agriculture. Let's focus on that number. So agriculture, remember, is expressed as a percentage, and the estimate is negative 0.1721. So we estimate an expected 0.17 decrease in standardized fertility for every 1% increase in the percentage of males involved in agriculture, holding the remaining variables constant. That would be the interpretation of our negative 0.17 coefficient. And if you look back, our t-test for that is significant. What I found interesting about this data set when I was kind of playing around with it, I just looked in R for some examples of multivariable regression data sets, and this one came up. But then, I ran the marginal estimate, the one that disregards all the other coefficients. So in this case, instead of doing fertility equals dot or tilde dot, which fits all of them in the regression model, I did fertility tilde agriculture, which only includes agriculture, and you see the estimate there is 0.19, but notice it actually reverses sign, and it's also significant. So that's kind of interesting. So let's talk about that. So one thing that's worth talking about is how can an adjusted estimate, how can an adjustment reverse the sign of an effect? And I go through a simulation here just to prove it to you that it can happen. You can look at the simulation settings up here, and what you see is that the relationship between x1 and y is 95, and then after I include x2, it's -1. And I did it so that all the p-values are ridiculously significant, 10 to the minus 68 and 10 to the minus 79. So what does this look like? What does this look like? Well, what happens here is here's y and x1, and this is the unadjusted one, and you see this nice relationship. But you also see that this other variable, x2, is really quite correlated with x1, right? So it's the color is x2. So when this, and the colors change along this gradient. So the relationship between x1 and y seems to be pretty related to this relationship between x2 and y. And what regression sort of does is it looks in a level of x2, and imagine within a level of x2, if you looked at them all, if the relationship was sort of linear in this kind of smaller dimension, it's sort of hard to visualize. So what we could do, remember, we've talked about this, is to try and remove the effect of x2 by taking it out of x1 by fitting a linear model of x1 is the outcome and x2 is the predictor, and taking the residual, so that's that guy, and then taking y where I fit y is the outcome and x2 is the residual, and that's that guy on this next plot. And you see that once you factor out x2, then you have a relationship in the opposite direction. And it's basically just saying if you were to kind of fix these colors, the colors are all binned, but if you were to sort of fix these colors, then what you would see is within a color a negative slope between y and x2 and x1. Okay, so it is possible, of course, when you adjust for another variable for this for a coefficient of interest to reverse its sign. So in this data set, the sign reverses itself with the inclusion of examination and education, both of which are negatively correlated with agriculture. Right, so the higher the percent scores for the higher the percentages for examination and education, the lower the percentage of males working in agriculture for those provinces. Remember, again, this is 1888. The correlation, in fact, is this negative correlation is negative 0.64. And education, by the way, I'm saying education and examination, but they're, these are kind of measuring the same thing. They have a correlation at 0.7. So the obvious question is, which is the right model? The marginal model that disregards education, or in this case, if you kind of put in these other things, it doesn't reverse sign, or the model with education and examination in there, which then causes this agricultural coefficient to reverse the sign. So which one, with those guys in or with those guys out, is the right model? Okay. So one could conjecture in this case is whether or not this positive marginal effect is an artifact for not, say, having accounted for education level. Now, how to interpret this is a little bit difficult, and it depends quite a bit on the setting. At the bare minimum, what one could say, and in this data set it seems reasonable, is that if someone were to fit this marginal model and were to claim that, let's see, where's the marginal model? Darn it. Oh, there it is. if someone were to claim that this marginal effect of 0.19 is conclusive proof that an increasing percentage of males working in agriculture reduces fertility rate, I don't know, for whatever the reason, there would be some skepticism. There would be some skepticism that you could, and criticism that you could levy at that model by saying, well, if you were to include education, not only does the effect not hold up, it actually reverses itself. Now, selecting the correct model is actually a quite difficult subject. There's several things that you would want to balance. One is, something that reverses the sign, but is kind of obviously meaningless from the context, is maybe not something you would want to include either. So the way to go about these things is a balance between the meaningfulness of the coefficient, a collection of model building exercises where you add and subtract covariates, and thinking along the lines of the interpretation. The way I actually like to do it more than anything else is I like, when fitting regression models, to kind of craft a story. And in this case, if my story was, I think that agriculture causes increased agricultural employment causes decreases fertility rates, what I would say is, okay, given my full data set, what would my critics obviously say of me? And in this case, my critics would have a lot of ammunition, and that would allow me to revisit my hypothesis. So that's usually the way I like to think about these exercises, but there's an entire branch of statistics called causal inference. And in that branch, they talk about how one can really try to navigate these thorny issues of taking observational data and trying to make more causal or mechanistic claims. Otherwise, you're kind of back to this sort of heuristic approach that I'm sort of advocating for, unless you're willing to take more classes and learn a lot more about this stuff. So let me just, I want to show another little fact so you know why these things pop up. What if I include not just unnecessary variable, but kind of clearly unnecessary variable? So the information from the variable agriculture is already, of course, contained in the model. Consider the model where we put in everything. But imagine if I created a new variable that is just this sum of agriculture and education. And clearly Z can't add any new information in this model. If we know the agriculture status of the province and we know the educational status of the province, then we know Z. Conversely, if we include Z and remove agriculture, then Z does contain relevant new information, because we need both agriculture. We need any two, whether it's Z, agriculture, and education. We need any two of those. We know the third. But including any two, if we were to include the third, it has to contain extraneous information, because we perfectly know it if we know the other two. So what does R do when we put in something completely meaningless in this linear sense? And that's this discussion only holds for things where it's linear, right? If I include agriculture squared, of course I know agriculture squared if I know agriculture, but that's not a linear function of the variable. At any rate, if you include a linear function of variables that are already in the model, then when R fits the model, it says, oh, wait a minute, you've already included variables that, if I know them, I linearly know Z, so this contains no extra new information, so I throw it out and I put an NA there. And so that's why you see these NAs pop up in R, is because that variable is linearly related to the other variables that are included in the model.